Welcome to our video summary on the gears with no teeth. How liquid robotics will change everything. If you find this content a real-time saver to explore new ideas, please hit the like button and subscribe for more. For over 5,000 years, one machine has been the silent, driving force behind human invention. It turned the wheels of ancient chariots. It ticks inside our most intricate clocks, and it gives power to our most advanced robotic arms. I'm talking about the gear. A wheel with teeth, interlocking with another to transfer motion. Its design is so fundamental, it's barely changed over millennia. But what if we could break it? What if we could build a gear with no teeth at all? A gear made entirely of liquid. How could you possibly transmit precise motion without physical contact, without the very parts that define what a gear is? Today, we're going on a journey that starts with this radical, seemingly impossible concept, and ends in a future where our most advanced robots are powered, wired, and healed by a liquid that is metal itself. The concept of a liquid gear isn't science fiction. It's a demonstrated reality from a university lab. At New York University, physicists showed you don't need solid teeth to transmit power. In their experiment, they submerged two simple cylinders in a thick mix of water and glycerol. When they spun one cylinder, the currents it created in the fluid caused the second cylinder to rotate as well. No physical contact, just liquid transferring energy with remarkable precision. What they discovered next was even more incredible. By simply changing the distance between the cylinders, they could create two different machines. When the cylinders were close, tiny vortices in the fluid caused them to spin in opposite directions, just like a traditional two-gear system. But when they were spaced farther apart, the fluid looped around both cylinders like an invisible belt, pulling them in the same direction. One setup, two machines, a gearbox and a belt drive, powered entirely by fluid flow. The implications are profound. This contactless mechanism solves some of the biggest problems in mechanical engineering. In a traditional machine, a single grain of sand can grind it to a halt. In a fluid gear, the liquid just flows past any obstruction. It's essentially unjammable. And because the parts never touch, there's no friction, no wear and tear. You could even change gear ratios on the fly just by adjusting the fluid's speed or viscosity. This is a revolutionary way to build machines. And its perfect partner is soft robotics. The vision of soft robotics is to create flexible, safe, lifelike machines. The reality is that these soft bodies are often powered by rigid motors and bulky, hard-edged gearboxes, creating pinch points that are a major safety hazard. Liquid gears eliminate this problem. Since the moving parts never touch, the mechanism is fundamentally safer to operate around people. This technology also allows for a new design philosophy. Instead of bulky gearboxes at every joint, a designer could power a flexible arm through a single shared liquid circuit. A network of fluid gears could be embedded throughout the robot's body, distributing power like a fluid-based nervous system. This is revolutionary with a simple fluid. But what happens if that fluid is something much more advanced? This is the next great leap. Gallium-based liquid metals. At room temperature, these alloys are both a flowing liquid and a highly conductive metal. Unlike toxic mercury, gallium is safe to handle. When exposed to air, it forms a thin, flexible oxide skin, like a water balloon with a liquid core. This allows the liquid metal to hold shapes and stick to surfaces, something a normal liquid can't do. Its properties seem purpose-built for the future of robotics. It can act as wiring, it's deformable, and it can even self-heal. Researchers are already using liquid metals to build the unbreakable robot. One of the most exciting applications is in self-healing electronics. They create a material with tiny liquid metal nanoparticles, each in its own oxide skin. When the material is cut, the pressure ruptures the particles, releasing the liquid metal. The droplets merge and instantly form a new conductive path, healing the circuit at room temperature. By mixing these same particles into a soft elastomer like silicone, engineers can create a highly conductive and incredibly stretchable electronic skin. It can be stretched to many times its original length while staying conductive, perfect for soft sensors that monitor a robot's movement. These individual breakthroughs are the building blocks for a final, unified vision. So let's put it all together. Imagine a soft robot, where the lines between structure, electronics, and power are completely blurred. It's a machine animated by a single, multifunctional liquid metal. This liquid acts as the hydraulic fluid for a network of jam-proof liquid gears. It flows through the robot's limbs like a vascular system, serving as the wiring that transmits power and data. As part of a composite skin, it functions as a vast network of stretchable sensors, giving the robot a sense of touch. And its self-healing properties allow it to automatically repair cuts, shrugging off damage that would cripple a conventional machine. The robot becomes less a collection of parts and more a single, integrated system, like a biological organism. We've gone on an incredible journey from challenging the 5,000-year-old gear to envisioning a robot built from functional fluids. The future of robotics may be less about solid steel and more about smart, responsive liquids. We are at the dawn of a new age, where the line between the mechanical and the biological is starting to blur, creating machines that don't just move but flow. Let us know your thoughts or suggestions for future content in the comments. Thanks for watching. We'll see you in the next one.